All right, so I will start. So hello everyone. My name is Alina, or for Chinese speakers, Ming Chi. So today I'm going to present generative models, mostly in the application of speech, to be exact, speech enhancement. That's what I'm working on. So before I start, some slides about myself. So also I'm one of the organizers of LauzHack and currently a PhD student here. So I was born in China and grew up in China. Then I did my bachelor study in Germany. Um, at that time, I was majoring in robotics and intelligence system. And during my bachelor study, I did an exchange at Carnegie Mellon University in the States, where I get exposed to more hands-on for robotics as well as computational perception and computational photography. So you will see that I have quite diverse background, worked on different stuff before. Yeah, so then moving on, I came to Switzerland for my master's study. So I've been doing projects applying deep learning to rehabilitation after spinal cord injuries. And also I did an internship in Tokyo working on computational imaging. Did another internship in Lausanne as well, working on NLP in hospital setup. So it's about information retrieval from electronic health records. Yeah. So right now I'm doing my PhD at Bethel, also affiliated with EDIAP. So EDIAP is some advertisement for the institute. It's a research institute in AI, and it's located in Valais, to be exact, in Martigny, and that's where it is. Yep. So at the institute, it's all about AI research, and it's ranging from speech, gaze, imaging to robotics. And there are like about 200 researcher, engineer, PhD student, postdocs, etc. My research is on deep learning for postlogical speech enhancement. You will know what it means exactly a bit later in my talk. Yeah, and currently for all different research labs, we have openings for semester project, internship, even research assistantship. And if you want to know more about the projects, feel free to check the links. Yeah, disclaimers, those PIs are pretty busy people. If you don't receive any reply, don't panic, be patient. If you're not patient enough, you can talk to me. I can try to help you, but I can't guarantee. Yeah, so then let's get started. So we have seen generative AI flooded in our lives. There are more and more applications coming out every second, every day, every minute. So despite the famous ChatGPT, we can see like, for instance, in different fields, for instance, in text, in video, in image, in code generation, speech generation, and 3D modeling generation, as well as in helping to kind of speed up research. There are different tools in different areas. And despite all these applications, let's look at the foundation of all this, that is the generative models. So here is a brief overview of different kinds of deep generative models. So for a start, you might already know, just a bit of refreshing your mind. Like generative models, they're a class of unsupervised machine learning algorithm that they are learning the underlying probability distributions for a training data set. So unlike the discriminative models that are predicting labels or getting a classifier, generative models aim to generate new data instance from the same distribution as the training data. So you have covered GANs yesterday, I guess. So they use a discriminator to distinguish real from generated data. And today we're going to mainly focusing on VAE and diffusions. So VAE stands for variational autoencoder, and they learn a compressed representation of the data to generate new samples. So there are also flow-based models, directly transform the data distribution. So the restriction is that it has to be invertible, and therefore there are few architectures that could do this. Also, they're usually quite parameter heavy, so it takes a long time to train, to inference, etc. And then there are diffusion models, which briefly speaking, gradually add noise and then reverse the process to generate data. So finally, there are also attention mechanisms focusing on different parts of the input, which you see a lot in multimodal processing as well, because with the attention has, it's easy to fuse different modalities. So as you can imagine, input and output can be from different modalities or even multimodality. For instance, with image generation would be text as input, which is the X in this diagram, and the output Z could be, or the X prime could be either image, then it's image generation. Then in broader view of speech, if the input is text, output is speech, then it's TTS, text to speech. If the input is speech and then the output is text, then it's ASR, automatic speech recognition. And then if our input is the noisy speech and the output is the clean speech, then it's speech enhancement or source separation. So what about speech? Why is it specific, or why I'm interested in it? So it is a fundamental aspect of human communication. So it will enable the exchange of ideas, emotions, as well as information. However, the real world environments are contaminated by noise. For instance, we can hear how it sounds like in noisy environments. You don't hear it? Let me try again.
Stocks also plunged on rate fears, period.
So here is with a moderate level of noise, you can still understand. However, when the noise level is quite high.
In addition, the bank has always pursued a policy of keeping its balance sheet relatively liquid with insiders and competitors selling.
Can anyone tell what is being said? Right. That's why we need this research. Yeah, so that's why it is important for us to have speech enhancement algorithms to be able to have more intelligible speech, and it will also decrease the cognitive load for human listeners. Right, so what is speech enhancement? So there are various aspects in speech enhancement. For instance, like in a broader speaking, denoising, like what I just played, it's actually using a clean speech, adding a noise on top of it. And then in order to remove the noise, it's a process denoising. There's also something called dereverberation, which means like in a room such like this room, when I'm talking, there's the echo, the bouncing of the sounds. Then in order to remove them, that's also something called reverberation. There's also bandwidth extension as well as declipping. It's some different artifacts during sound processing, or if you have a bad microphone, that's something that you want to improve on. So usually for speech enhancement, it's a general term, including all of them, but some people use denoising, dereverberation differently, like separately. There are also like for speech enhancement algorithms, some of them tackle only one aspect and some of them are universal. And since last year, there's more of a call for research community that we want more generalizable, robust, as well as universal algorithms or approach to tackle these questions. Right, so speech enhancement can be used for various applications such as voice recognition, teleconferencing, hearing aids, and voice controlled agents. So maybe you haven't noticed, however, like for instance, when during a Zoom, it's already some speech enhancement algorithms running in the background, which makes it easier to listen to whoever is speaking. Yeah. So here's a recap of the slides from Peter from yesterday. So there are various voice technologies. And despite speech enhancement being a standalone topic, it could be also a valuable preprocessing procedure for various downstream speech tasks such as voice activity detection, speaker diarization, keyword spotting, as well as voice classification. There's also more and more emerging topics into using speech as pathological detection tools. That's also what one of my colleague is working on. If you're interested, feel free to contact me. Right, so let's start with some of the details of the techniques. So the first is the VAE, short for variational autoencoder. So it actually is less similar to autoencoder that you have seen yesterday, but it is more connected with variational Bayesian and graphical models. I will try to use a minimum mass to explain. If you get confused, feel free to let me know. Yeah. So VAEs are generative models that learn a latent representation of data, so that from this latent representation, you can sample to generate new data from this. So more specifically, the deep speech prior is based on the decoder of the VAE. That is what I'm showing here, because currently I cut the encoder part. First, assume a latent variable z that we know, which is a latent representation of clean speech. Yeah, then we are generating new speech from this latent representation. And in the Bayesian theory, we have the prior, the likelihood, and the posterior defined on the right side. So we will have two steps. First, we sample a latent variable from a prior distribution, and then a value is generated from a conditional distribution. There are lots of maths involved for a full mathematical proof or derivation. There are several research papers to look at, so I'm not doing it here. And then the optimal parameter is the one that maximizes the probability of generating real data samples. However, this optimal parameter cannot be achieved in reality. Why? Because in order to have that, we need to think about and sum all the possible likelihoods, which is not possible in reality. And then to narrow down the value space to facilitate faster research of such of a optimal parameter, we're going to introduce a new approximation function. So the latent representation, the decoder is trained from the clean speech, adding the variational autoencoder. More specifically, an encoder network is introduced to estimate the latent representation. So we have clean speech, and we're learning this latent representation. And from the latent representation, we're predicting new samples. And with the new samples, we're going to find the evidence lower bound in order to train a better encoder, better latent representation, a better decoder, etc. So here with the elbow, the first term in the objective function refers to the regularization error in the latent space to ensure that we have meaningful latent representation. And then the second term here is to have a smaller reconstruction error from the predicted speech to the clean speech as the input. So in summary, the decoder network is used as a powerful representation of the clean speech spectrum. Yeah. Yeah. What do you mean?
Like you said, evidence lower bound.
Yes, so it is actually when you're calculating the loss function. So you're calculating the negative log likelihood, and you're going to maximize this negative log likelihood. And for this distribution, in order to find the maximum of the negative log likelihood, then you have lower bound that is bounding so that you can find the maximum value below this lower bound. It's a bit tongue twister-ish. Yeah.
And can you tell me what's ST? So ZT is the latent representation and S?
Yeah. So here S stands for, because they're from two different papers, I just try to explain. So here S means the clean speech, and which is actually the X in the prior likelihood and the posterior. It's a bit confusing. Yeah. More questions?
The prior is that normal or is there's like a scale diversion? Like I don't quite know what the prior is.
Yeah, so P of Z, in order to simplify, we consider everything as a Gaussian. So here we can easily calculate the prior because it will be just a Gaussian. So the key about training the variational autoencoder, which I didn't put in my slide, is it's actually we have a reparameterization trick. I can't pronounce the word. Yeah. So the trick is that instead of having a random latent representation, it is using the randomness in the mean and the arrow term, the epsilon, in this Gaussian distribution.
I'm sorry, could you repeat
so
or
intuitive
elaborate
is-
on latent representation, please?
Sorry, can you repeat?
I'm sorry, could you a bit elaborate or re-explain about what is a latent representation? Like what is Z down there on the previous slide?
So this zeta, so here in variational autoencoder, zeta, actually we need to select the dimension. So to some extent, it is a dimension reduction. So we try to find some representation that is with lower dimensionality that is going to represent the clean speech spectra. So here we, in our research question, we use clean speech spectrogram as the input. So we are going to learn a lower dimension of the clean speech spectrogram, so to say.
Yeah, thanks, okay.
Right. Then let's continue. So what are the pros and cons for the VAE? So first, for the advantage of VAE is because of this dimension reduction. So it's actually fast to compute compared to other methods like diffusion you will see later. So it is flexible and you can choose the dimensionality of your latent representation, which then you can also you can also look into this latent representation to see what is being encoded actually. However, the disadvantage is that with this inexact likelihood calculation, as well as this dimension reduction, in order to see it better, I use image generation as an example. So for the image generated with VAE, they're usually quite blurry. So this is not due to low resolution of the image, but this is actually blurry due to generation with the VAE. Then for speech enhancement, we want a clear speech. We don't want even noisier speech than we're doing speech enhancement before. So how are we going to deal with it? So to overcome such difficulties, we are using semi-supervised, or in other words, the hybrid method. So we are actually using the VAE to only learn a good speech prior, and then we use this to plug in a traditional method, Wiener filter, which dates back to the 1979. It's quite long ago and have been in the field for speech enhancement because it's usually with traditional signal processing method. So what the Wiener filter is doing is that we have a speech spectra denoted by the green part, as well as an estimate of the noise. So there, in different methods, there are also ways to estimate the noise. However, in my research, we have take a fixed noise which is modeled by the NMF, which is done for non-negative matrix factorization. So actually with the speech, you can also model with non-negative matrix factorization, but it is less accurate as the VAE. And so for us, the noisy speech is given by adding the noise on top of the clean speech. Then we have also the clean speech as something to compare with to see how good our enhanced speech is. Yeah, time for question. Yeah. Yeah, so because VAE is generative model and the NMF, it's a supervised model. So we're combining it. So some people call it semi-supervised, some people call it hybrid.
So it's like the VAE generated this on
No, it's not like that. It's just part of the model is being fixed and the other part are being more stochastic to some extent. Yeah.
Yeah, actually, and maybe I didn't quite understand it. Like, what's the pipeline? VAE is generative. You have speech that you want to denoise. How do you use VAE?
Yeah, so the VAE is generating a clean speech spectra. So it's like the VAE is used to generate a clean speech distribution. And here is more likely a distribution over the sum of two distribution. So this hybrid method is not the state of the art, but it could be a good introduction to later diffusion models because there is like a connection between VAE and diffusion models. It's just one of the, this is like the VAE and NMF part. This kind of hybrid approach was used more in 2018 to 2022. And right now we're kind of in the diffusion era, so to say. Yeah, it's just a bit of a history, but not really history, because the history would be like totally like Wiener filter, like back in the 1980s. Yeah. More questions? Then we can start with the diffusion models. So for diffusion models, I'm going to show you some videos. So I'm going to show part of the video. If you want, you can find the link once I posted the slides. I will post after this session. So basically for diffusion models, it started with a DDPM, which I can show a brief. So the DDPM is a connection with the VAE. So let's go back to this image. So here we have the VAE model. So what if you increase the latent dimension of Z? And for each step from x0 to x1, it is a whole process of from x to x prime. Then it's kind of a hierarchical VAE, which becomes a step in the diffusion model. It's a bit less explained, but you will see in the videos. So this is one stream, which is from VAE, making it hierarchical, and each diffusion step is a Markov chain. And the other method that starting with the score-based model, and then they made a connection in 2021 that it's the score-based method is actually also the diffusion model. I will show two videos and then you will see the connection.
That brought diffusion models into the spotlight is called Denoising Diffusion Probabilistic Models, or DDPM, by Jonathan Ho and collaborators, and it was published in 2020. Despite its reputation, this paper did not introduce diffusion models, nor did it coin the term. The earliest known reference to diffusion models as we know them comes from a 2015 paper titled Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics by Yasha Sol-Dickstein and colleagues. In 2015, GANs were considered state-of-the-art in image generation research, and diffusion models received little attention. In contrast, the 2020 DDPM paper quickly gained traction. It is now the most cited work in the field, with more than 20,000 citations as of 2025. If you look up diffusion models on any search engine, this is probably the first paper you'll come across. The main contribution of this paper was to take diffusion models from a theoretical concept previously limited to simple toy datasets into a state-of-the-art technique for image generation. On the technical side, it mainly introduced a much simpler training objective compared to the 2015 version. This made the method more accessible and highlighted interesting connections to earlier works on denoising models. Now let's break down the core idea. In the context of data generation, we start with a probability distribution P of X, which represents our training data. For instance, in the case of images, we can think of this distribution as representing all natural images, or even just a subset of natural images containing only faces. Of course, this distribution is so complex that we can't really find a single expression to describe it completely, and there are probably no such expression anyway. But even without an explicit formula, we still want to generate new images, which is equivalent to sampling new points from this underlying distribution. So the challenge is to find a way to create new samples without actually having a good, comprehensive way of describing the distribution. Diffusion models tackle this problem with a seemingly unrelated process by removing Gaussian noise from images. First, we gradually corrupt the images by adding Gaussian noise. At each step, a small amount of noise is added, slowly erasing the structure of the image. If we continue this process for many steps, the image eventually turns into pure noise. The key idea is then to train a model that learns to slowly reverse these steps and remove the noise bit by bit. If the model is effective, it should be able to start from random noise and refine it step by step into a meaningful image. Now let's see how the DDPM paper formulates this process mathematically. Let's begin with an image which we'll call x0, since it's the starting point of the noising process. For now, this image does not contain any noise. To generate the next image, x1, we use a conditional distribution, q of x1 given x0. We produce x1 by adding some amount of Gaussian noise epsilon. The amount of noise is controlled by a scalar value, beta. Then actually the distribution describing x1 is just a Gaussian centered on x0 with noise of variance beta. So rather than seeing this as adding noise to x0, we can just imagine that we take a sample from a Gaussian distribution of variance beta centered on x0. Then to go to the next step, we do the same thing, where we go from a given step to the next. Obviously, we'll need to change the mean of our distribution at each step. And so we'll need a coefficient in front of the mean to make it decrease to 0. This magic number that we will use is square root of 1 minus the variance beta. Well, why do we choose this number in particular? To be honest, multiple other valid choices exist. However, the authors of the DDPM paper specifically opted for this coefficient. The main reason for this choice is probably its simplicity. I'll skip the derivations because this is quite honestly pretty boring, but the important thing is that this choice results in a straightforward and convenient expression for the conditional distribution at any time step. So to go from the noiseless input x0 to a given time step of our diffusion process, we just have to apply this little formula. It depends on the term alpha t bar, which is simply defined as 1 minus beta, raised to the power of t. Now, does this thing actually converge to the normal distribution? Well, if we choose beta strictly between 0 and 1, it's easy to see that alpha t bar will converge to 0 as t grows to infinity. Then the mean of the conditional distribution goes to 0 while the variance goes to 1. And just like that, we finally have a proper variance preserving diffusion process. So this formula is supposed to take our distribution of data p of x and slowly transform it into a normal distribution. Let's see this on a simple 1D example. Let's say this is our original noiseless data distribution P of X. After applying just one diffusion step, the distribution barely changes. However, if we repeat this process for about 100 steps, we can clearly see the effect. The mean approaches zero, and the spread of the distribution stabilizes. And the nice thing is that we can go directly from the input distribution to any time step directly without iterating through all the previous steps. Now, if you've explored the DDPM paper yourself, you might have noticed they use a slightly different definition for alpha bar. In practice, diffusion models commonly apply varying amounts of noise at each step, rather than a fixed beta. Indeed, any noise schedule can be chosen as long as each beta remains between 0 and 1. How does that fact impact our formula to go from the noiseless image to any time step? Well, when beta varies at each step, alpha bar at step t simply becomes the product of 1 minus beta at every previous step, which is the expression you can find in the paper. So we have now defined a proper diffusion process that will progressively transform any distribution into a normal distribution. Let's now move on to how we can reverse this diffusion process using a neural network. Just for the sake of illustration, let's represent once again the forward process that enables us to go from our clean image x0 to a Gaussian noise sample xt using the probability densities q. Now let's assume there is a way to reverse these individual steps, and let's represent it with a probability density p, which produces xt minus 1 given xt. So, just like we defined conditional distributions q to go forward from one step to the next, we now define conditional distributions p to go backward in the opposite direction. While in the forward process all parameters are fixed, for the reverse process, our goal is actually to find the best parameters theta that allow us to remove the noise effectively. And as you've probably guessed, these parameters theta will be the weights of a neural network. Now you may ask, how do we train this neural network? Well, we'll adopt a very standard approach in Bayesian statistics, which is to minimize the negative log likelihood of producing a sample with our model. If you're not familiar with these types of objectives, don't worry. It simply means finding the set of parameters theta that maximizes the likelihood of generating real samples x0 from our data distribution using the neural network. But instead of maximizing p theta of x0 directly, we minimize the negative log likelihood, which in practice is easier in many cases. Okay, before we go further, let's define some useful notations clearly. The joint probability describing the distribution of all the variables from x1 to xt given x0 represents our complete.
Here starts the math part. Anyone wants to watch? Yeah.
Forward process. Using Bayes' theorem, we can decompose this joint probability into individual conditional distributions. And the neat thing is that since our forward process is a Markov chain, each noising step depends only on the previous step, which simplifies these conditional probabilities. Another notation we use is that instead of writing 3 dots every time we want to mention the complete forward process, we use this simplified version with 2 dots. And now let's rewrite this product in an even more compact form using the standard notation for products. We use the same compact notation for the joint distribution describing our complete reverse process. As you may have noticed, the reverse process is not conditioned on anything. Indeed, we will start from pure Gaussian noise without prior knowledge, whereas the forward process requires an input image x0. Okay, now that we have expressions describing clearly our complete forward and reverse processes, let's try to find an expression for the negative log likelihood. Generally speaking, when dealing with joint probabilities, a useful first step is often to marginalize the distribution with respect to the other variables. Doing this gives us that p theta of x0 is simply the integral of the joint probability with respect to all the other variables. Now, could we compute the likelihood using just this formula? Well, no, not really. What this integral means is that to compute the probability that our neural network generates a sample x0, we would have to sum over all possible paths capable of generating it. Let's visualize it this way. On the left, we have the density of natural images, and on the right, the pure Gaussian noise density. We know that there are paths connecting images to noise, such as our forward process, and we assume that there exist paths connecting noise to images. The formula tells us that we should sum over all these possible paths to obtain the negative log likelihood. Of course, there are way too many possible paths for us to compute this quantity. We say this quantity is intractable, meaning we can't realistically compute it exactly. Okay, but that does not mean we can't compute the negative log likelihood at all. Let's now use a very well-known trick. We multiply and divide by the density representing our forward process. We can rewrite this integral as an expectation, making the expression slightly more compact. And here comes another very well-known trick, Jensen's inequality. Since the negative log function is convex, we can put the log inside the expectation at the cost of introducing an inequality. And now we obtain an upper bound on our negative log likelihood, often called the evidence lower bound or elbow. Why is it called a lower bound? Well, since it's an upper bound on the negative log likelihood, it corresponds to a lower bound on the likelihood itself. Now, we'll try to make sense of this training objective by modifying and simplifying its expression further. I'm going to skip the detailed derivations here because they're honestly a bit tedious, and the video is already pretty math heavy. Just know that with some straightforward algebra and Bayes' theorem, we can rewrite the elbow from this form to this more useful expression. If you're interested in the full computations leading to this expression of the elbow, it's covered in part A of the supplementary materials of the DDPM paper. It's actually quite detailed and worth checking out if you're curious. Now, this new expression might look intimidating at first glance, but as usual, there's some intuition behind it. The first thing you might notice is the Kullback-Leibler divergence term, which we refer to as DKL. The Kullback-Leibler divergence is a way of measuring how close two probability distributions are.
This is also what is used for VAE as well. The KL divergence is like measuring a distance, but just between two distributions.
You can think of it as a kind of distance in probability space. If the distributions are very different, for example, they have different means or variances, the KL divergence will be large. On the other hand, if the distributions are very similar, the KL divergence becomes small. And it actually reaches zero only when the two distributions are exactly the same. So going back to our loss expression, we see that it's essentially measuring how far apart certain probability distributions are. Before we see what these distributions are, we can simplify this expression further. The first term on the left doesn't depend on our model parameters, so we can ignore it when optimizing the model. The last term on the right does depend on the weights of the network, and it measures how likely the model is to reconstruct a clean image from a slightly noisier one, more precisely from x1 back to x0. But remember, in diffusion models, we usually take about 1,000 denoising steps. So by the time we go from x1 to x0, there's barely any noise left. The model has already recovered most of the image. As a result, this term is pretty small and doesn't provide much extra learning signal. In practice, including it in the loss makes little to no difference, so we usually drop it from the final loss. That leaves us with the main part, a big sum of KL divergences between some distributions. We know that p theta of xt minus 1 given xt is our reverse diffusion step. But what exactly is this other distribution, q of xt minus 1 given xt and x0? Well, this distribution is what we call the true posterior. If we have our forward process, q of xt given xt minus 1, we know there's a reverse process, which we're trying to approximate by adjusting the parameters of a distribution p. Now, if we also condition on the original image, x0, we can actually compute the exact reverse process. This true reverse process, which uses the clean image x0, is what we call the true posterior. And the nice thing is we actually have a closed form expression for this true posterior. You might be wondering, why do we need a neural network if we already have a closed form expression for reversing the noise? The answer is, using this true posterior is cheating because it requires us to know x0. And during inference, our goal is to generate x0 starting from pure noise. So
this is the main part for the DDPM. There is something called score-based diffusion model. I'm going to show us like just 2 minutes showing you the connection between this and the DDPM.
appears chaotic, we actually know the physical equations governing the movement of these particles. And even more surprisingly, the same equations are at the heart of the revolution behind much of today's generative AI. So let's see how we can use physics to reverse this chaos and generate brand new data in the process. Before we go further, you might be wondering why I make a second video on diffusion models, while we already covered them in the last video. Well, the reason is that diffusion models actually have two very different formulations. The first one, the one we covered last time, was popularized by Jonathan Ho in 2020, based on a previous work published in 2015. It is mostly based on variational inference, so the general derivations and framework are close to variational autoencoders. We defined a forward noising process using a Markov chain and learned to reverse it by training a neural network with the evidence lower bound. But a little earlier, in 2019, another line of work was being developed by Yang Song, following ideas from energy-based models and score matching. This formulation is based on a completely different mathematical framework, but also provided very good generation results at the time. Yang Song then introduced a fundamentally different perspective in 2021, which we usually call score-based diffusion models. Personally, I prefer this second formulation. However, keep in mind that both points of view describe the very same objects, and both of them are equally valid. So let's see what the score-based formulation is all about. In DDPM, we defined a discrete Markov chain to corrupt data step by step with Gaussian noise. The specific expression of this Markov chain was carefully chosen so that it converges to a normal distribution when we apply it a lot of time. And sure enough, with this expression, when t becomes very big, we end up with something looking very close to pure Gaussian noise. The time-dependent beta parameter controls how big each step is, meaning how much noise we add to the image. If we take big steps between each image, the neural network struggles to reverse this noising process. And if we take very small steps, we have to do a lot more iterations to reach pure Gaussian noise. Now, instead of thinking in terms of discrete steps, we'll take a whole other point of view. Let's think of this process in terms of very, very small noising steps. Now, at the infinitesimal scale, this is the expression describing our noising process. Okay, it looks kind of scary, but trust me, it is actually pretty intuitive. This is a specific kind of stochastic differential equation called an Ito equation. What does that even mean? Well, it's called a differential equation because it relates the variable x to its infinitesimal change over time. And it is stochastic because this expression contains a second term called a Brownian process, which is random. Let's think of this in terms of particles. The first term in the equation describes how the position of a particle changes due to a deterministic force, like a wind pushing it in a given direction. This term is called the drift, and it is completely deterministic, meaning that we can predict the exact path that the particle will follow. Now, as I said, the second term is random, and it is comprised of a Brownian process as well as a diffusion coefficient. These two terms capture all the tiny, unpredictable fluctuations in the environment, making the particle appear to move randomly. The diffusion coefficient is the function controlling the intensity of this random motion. If it is small, the particle barely moves, and if it is big, the particle makes big random jumps. When we combine these two terms, the resulting motion is neither fully deterministic nor entirely random. The particles generally follow the direction imposed by the deterministic force, but their paths remain influenced by random fluctuations. Let's now see which specific drift and diffusion coefficients correspond to the DDPM Markov chain. So let's first recall the expression of this Markov chain describing the noising process in the DDPM framework. We'll quickly demonstrate how this chain actually converges to the Ito equation we just saw, which will also reveal the drift and diffusion coefficients. The first step is to define a new quantity, which we'll call beta tilde. It's simple.
I will skip this part. Basically, you get the idea that actually for a DDPM definition of the diffusion process can be also transferred into the score-based diffusion. So what I want to show you is how this is applied to speech enhancement. So in short, the diffusion model just is a chain of diffusion steps that is slowly adding the noise, and then in the reverse process to slowly get rid of the noise. So for speech enhancement, there are different ways of doing diffusion because you can give it different input. For instance, as you may have already seen yesterday, that for speech, it can be represented as waveform or as spectrogram. So that's the two on top, which is using waveform diffusion as well as the STFT diffusion. So here we're using mostly score models because they're faster to train. However, for the DDPM, there is a faster to train version called DDIM. You can check the paper as well or check videos how it is different from DDPM and why it's faster. So also for diffusion models, at the beginning, there are people from CMU doing DDIM with diffusion. However, later people figure out with score-based diffusion, it can achieve better results. So that's how most of the research now are following the score-based diffusion paradigm. Except the waveform diffusion as well as the spectrogram as input for the diffusion, there's also different variations that are using latent variable and the diffusion process on the latent variables, as well as for the CQT, which stands for a constant Q transform. So you can think of it as just another way to represent speech. So to solve audio restoration tasks, so a diffusion model must be adapted to generate audio that not only conforms to the learned clean audio distribution, but also it needs to be a plausible reconstruction of a given corrupted signals. So what I mean here is like, for instance, when you're doing image generation, you give Sora or DALL-E like a description like, I want a cat. However, you don't know, you cannot control how this cat looks like. But for speech enhancement, we know that we have a noisy speech and we only want a cleaner version of this speech, not a random speech. So I forgot the reference here, my bad. I will add it for later when I publish the slides. So researchers in Hamburg, they're conditioning such a diffusion process on the noisy speech, in that you have a Gaussian distribution for the noisy version, and in the end, you're not for the whole diffusion process, you want a random Gaussian noise on top of conditioned on the noisy speech, and then you're going to generate the clean speech based on this noisy speech. In that for each diffusion steps, you're also denoising. However, on the score model, then you're going to give the noise schedule as well as also your conditioning input. Yeah, that's like a short introduction of the diffusion process used for speech enhancement. Is that clear, or any questions or? Then that's it for my part, and I will pass the stage to Peter.